Well, on today's show, we consider the product rule. It's so much fun, uh, except that the product rule works for derivatives and not for integrals. And there sort of ought to be a product rule for integrals. And in this section of our text, what Thomas from Beyond the Grave calls Chapter 8, Thomas takes us through a look at how to evaluate integrals that you never knew how to evaluate before. For example, how do we evaluate that? I mean, it's a product. And yet, there's something inside of you that says, I have to be able to know how to do that. I have to be able to know how to do that. That can't be that hard, can it? And sure enough, it isn't. So consider the following. Bill Nye the Science Guy. When you were in Calc 1, you took the derivative of a product, the product u times v. And you figured out that that was u times the derivative of v plus v times the derivative of u. That's what you figured when you were in Calc 1. Well, I'd like to do some things to that. You're like, I would like to also, but I would like to do some things to that that are mathematically appropriate. It is totally true that u dv dx is the derivative of the product minus v du dx. Yes? Now, back to Calc 1. You treated these as differentials at some point in Calc 1. And so what I'd like to do is I'd like to multiply through by the differential dx. And that's going to give me u times dv is some derivative of uv minus v times some differential du. And then I'd like to do the unthinkable. I would like to integrate everybody. And if we do that, then we get that the integral of u dv is the integral of the derivative of, well, that's just uv minus the integral of v times du. It is this equation here that we refer to when we talk about integration by parts. This is integration by parts. And the way this ends up going is on this side of the equation, the u and the dv are your original integral. In your original integral, you identify a u whose derivative you end up having to find, and you identify a dv whose antiderivative you need to find. And then we try this formula, see if things work out okay, and with any luck, this one is easier to work with. If this one is easier to work with, then we win. And otherwise, well, let's not think about that. So back to our example. Some of this has to be a u whose derivative can be found easily, and some of it has to be a dv whose antiderivative can be found easily, because we're going to identify a u and a dv and set that equal to uv minus the integral of v du. So I'm going to say that the u is x and the dv is the rest of it. And it has to be, because all of this has to be equal to all of this. So this is the u and this is the dv. Everything has to be underlined somewhere. So what does this mean? Well, if u is x, then du is dx. The derivative of u with respect to x is 1, and we kick that up. On this side, it turns out that any antiderivative will do just fine. So I'm going to pick negative cosine x. I could have added a constant at the end. It's okay. We'd have added it and subtracted it and been fine. So let's see what our expression says. The integral of x sine x dx is uv minus the integral of v du. That's minus cosine x dx. So I have to ask myself, is this easier to work with than this was? And the answer is yes. In fact, we know how to do that, and we are done. We are done. And you can check yourself. You can take the derivative of this, and sure enough, you're going to end up with x sine x. So we identify in our original integral something whose derivative is easy to find and something whose antiderivative is easy to find. And then we crank things out, and hopefully this one is easier to work with. Well, what about that? Oh, let's make it harder. Now, you say to yourself, I think I can do this. I think I can do this. The integral of u dv is u times v minus the integral of v du. So we'll let u be x squared. I don't want to be x squared. Well, too bad, because I know what your derivative is. And then we'll let this be dv, and any antiderivative will do. So we take the derivative of u and the antiderivative of dv. And what the heck is this? Okay. uv minus the integral of v du. And we have to ask ourselves, is this easier to work with than the thing I had originally? And the answer is probably. And I have a sense that if I were to try this process again, I'd probably be in good shape. So I got to make myself some room. And I'm going to try the process again. I'm going to let this be u and this be dv. Any antiderivative will do. There's a derivative. So that whole integrand is covered by the u and the dv. And I know that this is uv minus the integral of v du. And the question again, is this integral easier to deal with than this was? And the answer again is a resounding yes. So x squared e to the x, distribute, antiderivative. And we're done. And you can take a derivative of that just to check yourself and find out we're okay. Quick side note here. What if we had gotten to this point and said, you know, last time we picked the polynomial for a u, this time let's pick e to the x for the u and 2x dx for the dv. Well, what would that have done? Well, this would have reversed that process and ended us up right back where we left off. So if we start with the polynomial for the u, we want to continue with the polynomial for the u. We don't want to switch up what we use for u in the middle of a multi-step problem. Okay? Well then, how about this? antiderivative 9x squared ln x dx. Hmm. Now that's an interesting argument because if we do what we've always done, then that's there. And what do you do with that? We don't know what this is. So we're totally toast. Well, let's try it the other way. What if this is u? Because I know how to find that antiderivative. I know how to find that. And then the rest would have to be the dv. But that antiderivative is not that hard to find. Well, I wonder if that's helpful. So the integral of 9x squared ln x dx is uv minus the integral of, oh, look at you. Look at that. And because this question is as rigged as a Chicago election, this is exactly what you think it is. Works out real nice. Works out really nice. If I can do one more demonstration for us. Integration by parts also works with definite integrals. Integral from 0 to pi over 2 of x cosine x dx. We use integration by parts to come up with an antiderivative of this, and then just like with every other fundamental theorem problem, we sub, and subtract. So we'll let u be x. I don't want to be x. Well, that's too bad. And we'll let the dv be cosine x dx. Any antiderivative will do. And so the integral from 0 to pi over 2 of x cosine x dx is uv minus uv from 0 to pi over 2 minus the integral of v du. Is this easier to work with than that one was? Sure it is. So we've got x sine x minus cosine x. Wait a second. The derivative of cosine x is negative sine x. So, like so, between 0 and pi over 2. So now all we have to do is sub in. If we sub in the pi over 2, this is pi over 2 times 1 plus the cosine of pi over 2, which is 0, minus 0 times I don't care, minus cosine of 0. And so we get pi over 2 minus 1. And hopefully this is refreshing your memory on all sorts of wonderful things that a Calc 1 teacher tried to show you. A couple of things I'd like you to try before we gather. A couple of things you should be skilled with. You should know how to find the integral of ln x dx using integration by parts. You should know how to do that. And you should know how to take the integral from 0 to 1 of x times e to the 2x dx. You should come up with a value for this, and we can check that value when we gather in class time. Oh heck, I'll give it to you just to keep you curious. This should be 1/4 of e squared plus 1. Hopefully that's what you come up with. Okay, so we'll check ourselves when we gather in class, and I will look forward to seeing you. Enjoy the rest of your day.